mg is not quite enough.
We talked about this particular unit.
No, I mean, look at the pattern. When you write it, these things are equal. I got negative mgh final plus mgh initial equals negative u final plus u initial. What could we let u possibly be so that these would be equal to each other?
G.
MGH.
I heard G and then
Is it like MGH?
it is like mgh. If u is equal to mgh, then u final would be this, u initial is this, and then the signs also line up quite nicely. So if we let u equal mgh, this works. What is another solution that would also work?
WH.
Okay,
Coco.
we'll give her something more distinct. And I will say that the answer is obvious, but people usually don't think about it.
One.
All right, we're on a roll.
One.
On fire.
One.
Huh, there's a whole lot of things here that all, when subtracted, get me the same answer. So that's part of why I'm going for here is, what else could we do so we get the exact same answer?
One.
Timing's a little bit off there. All right. What's the difference between this and this?
One. No, it's not. They're one different. Their difference is one.
Oh, okay. Think about it in terms of looking this way.
Okay. Well. One's even, one's odd.
All right. Sorry, this is devolved, but to get from here to here, what'd you do?
Two and
To get from here to here, what'd you do? To get from here to here, what'd you do? More specifically, 5. From here to here, what do you get? Or what do you do? All right. So as long as I add the same thing to both sides, I still get the same difference. Therefore, what would be another solution here that would also work?
Add 5.
Okay, yes. That is one solution that would work. So if I put a +5 right there, I get the same thing because I'll end up with a -5 and a +5 and they'll cancel out. If we made it slightly more generic, more generalized, what will we add here?
Add numbers.
Yes,
Oh.
just some constant. Now typically when someone says what the formula for potential energy is for gravitational potential energy, assuming that little g is constant, is they'll just say mgh. In reality, it's mgh plus some constant. We generally ignore the constant because it's going to cancel out most of the time. But it gives us some flexibility here. Ultimately, what it allows us to do is decide we can make h equal to 0 wherever we want. Or more specifically, we can make potential energy 0 wherever we want. One location though, don't make it 0 to 2 completely different places. So, I got the ground here, I have my object initially, and we'll just say that's 2 meters. Let's give it a mass of 3 kilograms. And we'll put it on Earth 2.
Yeah.
Up here, let's say 5 meters. What is the potential energy, gravitational potential energy of the mass here?
You said, what is the gravitational
Potential
potential?
energy of the mass at this location. And don't forget units.
$60 joules.
Okay. Anyone have a different answer? All right, so we have one guess right now, one speculation of 60 joules. How'd you get 60 joules?
I said 3 times 10 to get my mg.
So you're doing MGH?
Yeah.
So you did 3 kilograms.
3 kilograms
That's
times
10.
10 meters per second squared. And then times 2 meters.
So from that, you got 60 joules.
60 joules, yes.
What is another correct answer?
60 Newton meters.
Okay, yes.
60 joules plus 5.
I assume 5 joules.
No, just 5.
There's 5, okay. Well, part of me wants to go, sure, that actually works, and part of me wants is cringing at the lack of units there, but it would actually work. Unconventional.
We're making it up.
Let's throw the joules in there just for the sake of what I want to
Plus
do right
5
now.
joules.
All right, so 65 joules. That, okay. What's another correct answer?
Like, couldn't you just do like 60 joules plus the constant?
Yeah, you can add whatever constant. Especially when you make the constant negative 60 joules. What's the potential energy there?
0.
Yes. So we could make H is equal to 0 here, which is what Ibrahim did to begin with, or as Kyle was intimating, we can make H is equal to 0 there, and just say it says 0 potential energy to start with. Whichever one you pick is fine. Just once it's set, we now have in place, we can't just suddenly change it in the middle of a problem. Because my next question is, what's the potential energy here? So let's first just do it with H is equal to 0 at the bottom. So my potential energy was 60 joules here. If H is equal to 0 here, what is the potential energy at this spot? Gravitational potential energy.
150 joules.
All right. If we let H is equal to 0 here, what's the potential energy at that spot?
0.
What's the potential energy here?
Would be
90 joules.
They are both correct, given the questions that I've asked. Because what really is important is the change in potential energy. If the object goes from here to here, so it goes from the lower elevation to the higher elevation, what is my change in potential energy? If I'm going from 60 joules to 150 joules, what's my change in potential energy?
90.
90 joules.
And if I go from 0 joules to 90 joules, what's my change?
90 joules.
Because that's the important part. The change in potential energy is the important piece. Questions up to here?
Okay, so where does negative change, or negative change in potential energy come in? Like, why do we have to specify that, like, where was it? That conservative work has to be the negative change in potential energy?
If I take this up to put a ball here and I lift it up, so I have to apply force to it in order to lift it up.
Right.
The work done by the earth, that's the conservative force. The work done by the earth is, because it's negative because that force is against the direction of motion.
I see.
When I let go, it's, the force of gravity is doing work now. So there's a negative change in potential energy because it's going a little closer to the ground. And yeah, that's the essence of it right there.
But it's always gonna be negative because it's moving against the desired direction of motion.
You think about it this way, that I've never really found this definition of potential energy to be helpful for me, but if it helps you. Potential energy is the potential to do work. If I lift the rock up to here, it's got this energy that's stored in it, and if I let go, we can see that energy, but in fact, as it changes to kinetic energy, it gets faster and faster. I guess in some sense, like hammering a nail. I mean, you start from here, you bring some force into it, there's some potential energy stored. I'm playing fast and loose with some of this. Energy stored in it, which we convert into kinetic, which then drives the nail in. So it's sort of cocking the gun, pulling back the bowstring. I mean, you're getting ready to do some work, and so by lifting the rock up, you're now allowing it to do something useful. Drop it on your enemy's head. Because, frankly, all physics true. It leads to weapons. So,
yeah.
So, you're putting potential into it. As it starts to perform its actual work, as we now turn function from this pulling back the bowstring. When we let go, the potential energy is turning into kinetic, which means it has to lose potential energy in order to gain kinetic.
I see what you're saying.
And so the negative is indicating that we're losing potential, in some sense. As the conservative force does positive work, we're losing potential energy because it's being converted.
So, is it kind of like you can't just go from like positive to negative, you have to go through zero kind of thing, where like you can't just go from, you can have positive potential and then get positive kinetic. If you have positive potential, then it's gonna be negative kinetic.
No, you can't have negative kinetic.
Oh, no.
Yeah, not like that.
Oh.
Let me go home in the bed.
Because it made sense what you said, like when it like it's losing, like the bow, it's losing kinetic energy and
Losing
or
potential.
losing potential energy and then gaining kinetic energy.
Right.
So, and then that losing is the negative part.
Yeah.
Yeah.
Alright, other questions?
Can you say what that first equation means again?
What that is?
Yes.
For every conservative force, there exists a potential energy. So if the force is weight, then your potential energy is mgh plus a constant. If it's the generalized formula for gravity, the formula for potential energy is negative big G, mass 1, mass 2 over R plus a constant. If it's elastic, the formula is 1/2 K, lowercase k, delta x squared. Electric, K sub E or C, whichever one you like. Q1, Q2, over R. And magnetic is complicated. So different, oh, sorry, plus a constant, plus a constant.
So what does the constant do for us?
It allows us to put 0, we can make it 0 wherever we want.
So we can just choose what the problem wants to be, like where we start the problem.
Yep.
Yes.
I also want to point out, referencing something that you had mentioned earlier, Jack. You said we didn't know which way was positive or negative. Well, in this case right here, I didn't tell you which way was positive or negative, and it doesn't matter. Because the way that we derived our formula, mgh, it assumed that the gravitational force was downwards.
Mhm.
So if I move an object from here to here, so let's say that I gain 90 joules of potential energy. The gravitational force is this way, my displacement is that way. If up is positive and down is negative, when I multiply, I'll get a negative number. If down is positive, that means up is negative, I'll still get a negative number. So which way is positive or negative does not affect the amount of work that was done.
That also leads to a negative potential energy.
Yeah.
Okay.
Or negative conservative work.
Negative.
All right, so let's do, not total G. Try that again. Not that. All right. What I mean here, we have this problem, a box gains 10 joules of kinetic energy, but the conservative work done on the box is 5 joules. So I want to know what is the conservative work, the non-conservative work, and total work done on the box. What is the change in kinetic energy, change in potential energy, and change in total energy of the box? And what is the conservative work done by the box, non-conservative work done by the box, total work done by the box? We have two somewhat independent pieces of information. We can figure out all 9 values.
So the conservative work, by box is 5 joules.
Ooh. Oh, that's the word on there.
No, then they're on the box, it's 5 joules.
All right, so I know that's 5 joules because that's given in the problem. What's the other piece of information given in the problem?
The block contains 10 joules
Of,
of kinetic.
so change in kinetic energy, 10 joules. The work energy relationships should give us the next two. What's the relationship between work and kinetic energy? Or changing kinetic energy?
What?
Pardon?
Did you say the relationship between the work?
And changing kinetic energy.
Okay.
What
Just
is-
the negative of the change. Oh, wait, never mind. It's potential.
Okay, then we'll go to that next. What's the relationship you're looking at, Carolyn?
The conservative work is equal to the negative change in potential energy.
Okay, so therefore, I know what the conservative work is, what's the change in potential energy?
-5.
Joules. All right,
Right. Oh, and we can do, so big E, energy, change in energy is kinetic energy plus potential energy. So 10 joules plus -5 joules is 5 joules.
yeah. I'm gonna change one of the numbers here, and I apologize for this, because later on, when you're looking through your notes, I don't want you to get confused about why this and that are the same thing. So I'm gonna change this 5 to a 6. So what's my change in energy now?
Well, the change in, potential energy is now -6
Right, and the change in total energy?
4
Yeah, all right. So
joules.